In this video we will discuss dynamic routing. Some of the things that will be mentioned are metrics, administrative distance, identifying different elements in the routing table, and different ways to classify our routing protocols. Dynamic routing has been around since the 1980s, starting with RIP. RIP was the very first dynamic routing protocol that was developed. As networks evolved, so did routing protocols. New ones such as EIGRP and OSPF were developed. We have even newer ones for IP version 6, such as ISIS v6 and ripping for the version 6. So as networks have evolved, so have dynamic routing protocols. Newer ones with better features have come about, such as the EIGRP and the OSPF. The function of dynamic routing protocols are to share information between routers. Essentially, with a dynamic routing protocol, what happens is the routers will exchange information with each other about the routes that they know and the routes that they have directly connected to build the routing table. You as the administrator do not have to enter in the static routes when you select a dynamic routing protocol such as RIP. They will automatically update the routing table when the topology changes. They will determine the best path to the destination, and they have the ability to find a new best path if the current path is no longer available. So the little diagram down there just shows that the routers are exchanging updates amongst each other, and from those updates they can then build the routing table and select the best paths. Just to relate dynamic to static, since we learned about static in the last chapter, I just wanted to compare static versus dynamic. Some advantages of the static routing that we learned about is that it can back up multiple interfaces on a network router. It's easy to configure. There's no extra resources are needed, and it's more secure because these updates aren't going to be sent back and forth. The disadvantages of static routing are that network changes require manual reconfiguration. If a network change were to occur, you'd have to manually go into the router and change your route, take out the old route, put in the correct new route. It does not scale well in large topologies. If you have multiple networks, multiple routers, that just increases the amount of IP route statements, the amount of static routes that you have to add. Advantages of dynamic routing: administrators have less work maintaining the configuration when adding or deleting networks. Those dynamic routing protocols will automatically pick up those changes. They react to the topology changes automatically. The configuration is less error prone. It's more scalable. Growing the network usually does not represent a problem here at all. Disadvantages of dynamic routing protocols is that the router resources are used. We have more CPU cycles, more memory, and more link bandwidth usage. So typically we need more powerful routers. More administrative knowledge is required for configuration, verification, and troubleshooting. When you get into the more advanced routing protocols such as EIGRP and OSPF, you have to have more knowledge about that routing protocol. You have to have more knowledge on how to configure and verify and troubleshoot it. Some of the easier ones like RIP don't require quite as much knowledge, but they're not quite as sophisticated either. Our routing protocols are typically classified into two main categories. There's distance vector and link state, and we will spend the next chapter talking about distance vector, and the chapter after that talking about link state. So we'll take each one of these individually, but just to give some information on each one. The distance vector determines the direction or the vector and the distance to any link in the network, whereas the link state, also called the shortest path first, recreates an exact topology of the entire network. With the distance vector, it's kind of like driving towards a destination. We look at the road signs, and if the mileage is getting lower, that means we're going in the correct direction. If the mileage started getting higher, then we know we'd be going in the wrong direction. Link state actually will create an entire map. They have an entire map of the network, and from that map they can choose what is the correct destination to take. Distance vector will pass periodic copies of the entire routing table from one router to the next. So they take their routing table, package it up, and send it to the other router. From that information they can build the routing table and converge. This is also known as the Bellman-Ford algorithm. Like I said, it's similar to the signs found at a highway intersection. A sign points towards the destination and indicates the distance to that destination. Further down the highway, another sign points towards that destination, but now the distance is shorter. So if you're going to drive from Bismarck to Fargo, when you very first leave Bismarck, it's going to say Fargo 189 miles. When you get to Jamestown, now it's going to say Fargo roughly 100 miles. So as that mileage gets lower, we know we're going in the correct destination. That's how the distance vector works. When do you want to use a distance vector routing protocol, such as RIP or EIGRP? You want to use it when the network is simple and flat and does not require special hierarchical design, when the administrators do not have enough knowledge to configure and troubleshoot link state routing protocols, when specific types of networks such as hub and spoke networks are being implemented, or worst case convergence time in a network are not a concern. Link state features, some common link state are OSPF and ISIS. We'll talk about OSPF in this curriculum, but OSPF can create a complete view or topology of the network by gathering information from all of the routers. It builds that complete map of the network. There's no need to look at road signs because we have this map. OSPF is a link state protocol, like I said, that we will learn about in this particular curriculum. When do you want to use a link state compared to distance vector? Well, when the network design is hierarchical, usually occurring in large networks, the administrators have good knowledge of the implemented link state routing protocol when fast convergence of the network is crucial. Just a quick chart here to compare the two again. Distance vector, typically easy to configure, very simple operation. A con is that it transmits entire routing updates amongst routers. Link state, once converged, sends only network topology changes. It maintains that entire map of the network, but it does require more memory and more processing power on the CPU end. You also need more knowledge as the administrator to configure the link state routing protocols properly. This chapter also talks about class full versus class less routing. With class full, the subnet mask is going to be the same throughout the topology. If I take a look at this topology here, it all has a /24. Same subnet mask throughout the topology. Routing protocols such as RIP version 1 is a class full routing protocol. If you have a topology that the subnet mask changes throughout, you're going to want to use a class less. With class less, the subnet mask can vary in topology. Routing protocols such as RIP version 2, EIGRP, and OSPF are class less. Convergence is when all routers are at the same state of consistency. Basically what that means is that all of their routing tables are going to look very similar, almost identical. They would have routes to all the networks in your topology. Convergence, the faster it happens, the more desirable it is. The lack of convergence can lead to routing errors and possibly loops. RIP and IGRP is an older routing protocol that's being phased out, but those have slower convergence. It takes longer for all three of those routers in that picture when using RIP or IGRP to have consistent routing knowledge, and that can cause potential problems. If I need faster convergence to happen, I'm going to want to use EIGRP or OSPF. They have faster convergence, which means all three of those routers there would have consistent knowledge, all of the correct routes in the routing table a lot faster. Metrics are discussed in this chapter. Metrics are basically just a value used by routing protocols to assign a cost to reach a remote network. What is the cost going to take to get to that remote network? The metric is used to determine which path is most preferable when there are multiple paths to the same remote network. Some of the different metrics that can be used are hop count, that's used for RIP. It can be used bandwidth, load, delay, reliability, and cost. So different metrics are going to be used for different routing protocols. And when we discuss each individual routing protocol, we'll discuss what the metric is. Administrative distance is also mentioned in this chapter. Administrative distance is the trustworthiness of the source of the route. The lower the administrative distance, the better the route. If I take a look at this picture here, if I want to go from router 2 down to PC5, I have two ways I can take. I either can go to the left and get down to here, or I can go to the right and get down to here. Well, which route is R2 going to install? It's going to install the one with the lower administrative distance. It would end up choosing the EIGRP route and going towards the left because it has an administrative distance of 90, where on the right hand side RIP has an administrative distance of 120. When two or more routes to the same destination have the same administrative distance and metric, load balancing will occur. If I take a look at this topology, and in this topology all of these routers are running RIP, and all of the RIP's administrative distances are 120. So now I can either go to the left and down or to the right and down. Well, which way do I choose? Typically I would choose which way had the best metric now. Could it be the left? Or could it be the right? Well, if the metrics are the same, what it's going to do is it's going to load balance. It's going to send some of the packets to the left and some of the packets to the right to get down to PC5. And when it load balances, your IP route or your routing table is going to look like this. You're going to have two destinations to that same network. So this is saying to get to that 192.168.60 network, to get down to this network that PC5 is on, I either can send to the 192.168.21, which is going to the left, or I can send to the 192.168.41, which is sending to the right, so it will load balance. So again, what a router will look at to determine what is the best path is first the administrative distance. With the administrative distance, whatever is lower, it will use that one over the one that is higher. When both administrative distances are the same, or I have the same administrative distance throughout my topology, then it will take a look at the metric. Which hop count is better, which bandwidth is better, depending on which routing protocol I'm using. If the metrics happen to be the same, like they are in this case, then we will have load balancing kick in. That is the end of this video. This video is just meant to give an introduction to dynamic routing protocols, explain kind of how distance vector and link state work, and then how metric, administrative distance, and load balancing work as well. All of these topics, link state, distance vector, and some of the specific protocols, we will get into more detail in future chapters. Thanks for watching.